So we're talking about sinusoidal graphs. And sinusoidal graphs have a certain shape and they have characteristics. And we'll talk about that in a few minutes. But there's some new vocabulary that comes into examining any type of trig function like a sinusoidal graph that has to do with this idea of being periodic. So we want to just look at some of the language for periodic phenomenon. Now, you might be able to think of periodic phenomenon. Can anybody think of something that repeats a pattern over time? Other than a math thing, other than a math example. Your sleep cycle. So if you have a normal, regular sleep cycle, what would happen? When you say sleep cycle, what are you measuring? During the day or during the night or over the course of 24 hours? And hopefully that's fairly stable, right? What else? What did we just do on Saturday or Sunday morning at 2 a.m.? You did homework at 2 a.m., okay. I just discovered I can look in each person's activity log. I didn't know that. And I can see the last time you were on, how long you were on for, whether you asked for help on a question. Boy, I can be such a voyeur in this class. It's amazing. So what did we do over the weekend? We changed the clocks. We sprung forward. So do we have some kind of regular pattern that has to do with the length of daylight throughout the year? Yeah, right? We know that on June 21st, the summer solstice is our longest day, longest time period of light. And then on the winter solstice, we have the shortest days. So and in between, it fluctuates, right? So this idea of periodic phenomena has some very specific vocabulary. So we say that if we repeat the same pattern over and over again, it's kind of like Groundhog Day, if you ever saw that movie. It's said to be periodic. So period, what we mean by the word period is it's the shortest horizontal length that repeats. So what is repeating here? What's repeating here is this shape that kind of looks like an M, goes down below, and then it looks like some kind of like maybe like curve, and then that repeats over and over again in both directions. So if we were trying to figure out what the period is for this particular function, you look for two corresponding points. So often people look for like the highest points and the lowest points. So for example, I would see right here that this would be my highest point in this first cycle of the red M. And then over here in my second cycle, let me make it blue, I would have that same corresponding point. So you want to measure the horizontal distance that goes right across there. You can look down on your x-axis and see you're going from 3 to 9 to get the answer 6. You could, in this case, count, assuming we know that each of these increased by 1, you could actually count the number of squares. But in this particular case, the period for this phenomenon would be 6. Okay. Let's erase that so we don't get too many things going on here. The midline is a horizontal line, so it's going to have an equation that looks like y equals some number. Anytime you report a midline, I don't want to see just a number, it's always an equation. Y equals some constant. So the midline is the line that goes through basically the middle pattern, right? The middle pattern that you see. So we see that we have a high here of 6, and what's our low? -1, right? So our range would be from -1 to 6, which is 7 spots, right? And halfway would be 3.5. So if you took 3.5 down from 7, from 4, you'd be at 1.5. Or If you go up 3.5 from -1, you would be at 1.5. So this is actually, it says axes here, but this is actually the midline. So that dotted horizontal line is the midline. Goes directly through the middle of your pattern, okay? Amplitude is a measurement of maximum vertical distance from the midline. So you can either say, okay, here's my midline, I'm at 1.5, and the most I can grow up is to 4. So 4 take away 1.5 is 2.5. So my amplitude is 2.5. You could also go from your lowest point up to your amplitude, up to your midline, thank you. And that's also 2.5 spaces. Okay. So those are the 3 major ideas we're going to talk about today for sinusoidal functions. And for sinusoidal functions, we're going to talk about graphing sine theta and cosine theta today. Okay. All right. So let's move on here. We're going to start with this idea of a Ferris wheel. And just to make our scales very easy today, we're going to just change that diameter of 24 meters to 20. Okay. Okay, so this Ferris wheel, and if you look in your book, now almost every single pre-calc book has this picture of the London Ferris wheel. If you've ever seen pictures of London, there's a huge Ferris wheel that's right along the river there. I went to London back when my daughter was 5, so that was almost 19 years ago, and there was no Ferris wheel then. So this is a fairly new construction. And this Ferris wheel, so in the books, they have pictures and lots of examples of this Ferris wheel to get this idea that we're going to talk about today. But let's just say we got any Ferris wheel here. And I didn't know until I was typing this up last night, late last night, that Ferris, you have to capitalize because that must be the name of the person that invented these Ferris wheels. So anyway, that was just new to me. So it has a diameter of 24. So that means the distance from the center out to the, oh, see, 10, 10, 10. The radius then will be 10 because the radius is half of the diameter. So 20 divided by 2 is your radius, which is 10. Thank you. Okay, so it's rotating at 3 revolutions per minute. Okay. And at its lowest point, it's 5 meters above the ground. So that occurs right here. That's a distance of 5 meters. Okay. That's the lowest point. Assume that the ride starts in the pictured position. So here's your little cage that you sit in, your little seat. And hopefully you're not with someone that swings it back and forth. Right? And we're going to say that that position we're calling time t equals 0. Okay. So let's make a sketch. Assume the ride starts in the pictured position. Let's make a sketch of the graph that models the height of the rider in meters as a function of time after the ride begins in seconds. So we're going to have t measured in seconds along your horizontal axis and height measured in meters along your top. So just like we do with the unit circle, we're going to divide up our axes here in certain time increments. So we know that at time t equals 0, how high above the ground are we? We're 15 because we've got the 10 meters of the radius and then the other 5 meters here. So t equals 0 is going to be a point that's not too bad. I'm just going to break this up into 5, 10, 15, 20, 25 like that. So we'll chunk that out. And so at time 0, I'm at 15 meters. All right. 0, 15. Starting time, starting height. Okay. Now I have to figure out, as I move, so remember, we're keeping track here of the vertical distance. When I get up to here, I'm at a vertical height. And then I get up to here, I'm at this vertical height, which is 25 meters, right? What I have to figure out is, what is the time right here? What time do I associate with that height of 25 meters? How am I going to figure that out? Anybody have any ideas? Okay, hang on. So we got 3 revolutions and 60 minutes. Is everybody okay with that? Is that right? 60 minutes? 60 seconds. All right, it's 1 minute. Okay. So we have 3 revolutions per 1 minute. That's the same as 3 revolutions in 60 seconds. How many revolutions are we going from time t equals 0 up to this high point here? How many revolutions? What fraction of this circle have I gone? 1/4, right? Because it's your first quadrant right there, right? So I've gone 1/4 of a revolution, right? 1/4. How do I do this? I don't know what to do now. All right, so then you make this into 1 revolution to 20 seconds. Okay, everybody all set there? 1 revolution is in 20 seconds. If we can do 3 in 60. Okay, so now we want to make a proportion. We want 1 revolution in 20 seconds. I want to know how long is it going to take to do a quarter of a revolution. So I have to find out this number down here, right? So you can either solve this by saying I multiplied 1 by a quarter to get a quarter, so I got to do the same thing to the bottom, or you can use your cross product idea for solving a proportion. However you are used to doing this, so you can say 1 times x is x, that's equal to 1/4 times 20. Either way, x is at 5 seconds. That's why I changed it to 20, so everything's in increments of 5. So now I'm going to chunk this out, 5, 10, 15, 20. That makes 1 revolution. So these are seconds, 5, 10, 15, 20. So at 5 seconds, I am at what height? 25, right? Because I've got this 10, and that 5. So I'm at 25 after 5 seconds. 5 seconds, I'm at 25 feet. Okay, it stopped to let some people on, and then we started rotating back towards, and we come down here. How long did it take me to get to here? Another quarter of a revolution. So from the beginning it's 10, right? Or another 5 seconds. So we're out here at 10 seconds. And what's our height again? Same as it was at the beginning, 15, right? So at 10 seconds, we're at 15. We go another quarter of a revolution. We're at 15 seconds. And now we're only 5 feet above the ground. So that's our low point. So we're at 15.5. And then we come back around, right back to where we started. So after 20 seconds, we're back at a height of 15. And guess what? We start the whole thing over again. We go back up, we come back down, we hit our low, we come back, right? This just repeats over and over again. Okay. So if I wanted to connect these points now, you wouldn't connect them with straight lines. Let's see if I have my magic pen here. That will disappear as magic. Yeah. You don't want to connect them like this, or you're going to have a very abrupt ride, right? When your velocity changes really quick from this to this. It's not this straight line kind of phenomenon. It's a nice, smooth curve. So let's connect these. Nice, smooth curve. Okay, so we go, here's our period, right? We started, our starting position and our ending position are the same. So that 20 seconds would be the period for this one cycle to happen, right? To go around all the way around one revolution. So our period here is 20 seconds. Does everybody see that? Or I could wait and do this next height here and then measure this height if I wanted. This would be 25, 25. Either way, any corresponding points is going to be 20 seconds. So that's our period. It's 20 seconds. The midline is right here, right? The midline goes straight through the middle. Right? When I draw from the beginning to the end, I've drawn a horizontal line that cuts your high point and low point, that distance right in half. So my midline here would be y equals 15. And my amplitude goes from my midline, which is at a height of 15, up to either my highest point or from my midline down to my lowest point. So that measures 10, right? So my amplitude is 10. Okay. So the last time I taught pre-calculus, we didn't have this Ferris wheel example, but it's a great example for you not only to understand that the idea of this periodic phenomenon, but also to get a visual of what happens to the height, your position as you go around. And then to get some help with these terms here. Any questions? Yeah, Jackson?
Well, I was wondering if there's
On what chart?
like on that.
Right here, this graph?
Yeah.
Yeah, it just you just usually do a couple of cycles of it, and then you put the arrows just like you do with a line or a parabola. You know, it continues with the same pattern. Okay. Any other questions? All right. So this following situation, if you notice at the very end for homework, I didn't say do previews because I didn't create another set of preview exercises for this since it's the same exercise. However, I want you to do 4A and B as your preview. And I'm going to get you going with this, and then I'm going to leave you to your own devices to finish it off. So here's a problem that describes a situation. There's lots of situations. I was hoping someone would say something about the tides, high tide and low tides, and that sort of periodic phenomenon that happens with the high tide and low tide. But here's a situation. The amount of daylight varies over the course of the year. The summer solstice, which happens on June 21st this year, is the longest day of the year. In Greenfield, there will be 15 hours and 18 minutes of daylight on the summer solstice. Now, if you go to different places in the country, depending on their latitude, you'll get different amounts of sunlight. The winter solstice is the longest day of the year in Greenfield, and there'll be 9 hours and 5 minutes of sunlight. Sketch the length of the day in hours, D, against the time, T, over a 3-year period. Okay, so to get us going, you want to put an set of axes, and T is going to be days, right? They could be days or they could be months. Maybe we should probably do months. We could do hours, we could do minutes, but we're not going to be that exact. We're just going to do months here. Since there's 12 months in a year, that should be pretty easy to chunk out. Okay, so that's going to represent months. And if we start at 0 months, how many months are we going to go out for 3 years? 36. So here I'm going to put 36. And I'm going to chunk it out into 3 equal parts to represent each of the years. Okay, so that's how I would start this. The vertical axis is daylight, the amount of daylight, and that's measured in hours. So one of the things you will have to do is you will have to convert hours and minutes to just hours. Okay, hours and minutes to just hours. So let's do one together. All right, you have 15 hours and 18 minutes. 15 hours and 18 minutes is the same as 15 hours and 18/60ths of an hour. And you can reduce that by dividing top and bottom by 6, which is 3/10. And then you can make that into a decimal, 15.3. So it would probably be typical to start this problem like on January 1st. And however, since we have these two particular data values, either for the longest day of the year or the shortest day of the year, I would suggest that your intercept, your vertical intercept, either be 0, 9 point, whatever the 5 minutes is. Well, we might as well just finish this off. 9 hours and 5/60ths of a minute is the same as 9 and 1/12. Does anybody know what that is as a decimal? 9.0, 9.2, 9.1, what is it? 9 what? 1/12? No, I don't should. All right, how about 9.08 with 3 repeating? Okay. So let's call that, let's rough that out to be 9.1, just to make our calculations easy, okay? So you can either start with 0 being the summer solstice and start at your high point, and then 6 months later, so we know we've got these 6-month periods between December and June, so those are going to be important points in our particular graph. Or you could start 0 at 9.1 at your low point and move up to your high point. So this is going to be your preview exercise for when you come back on Monday, March 26th. Okay, so let's move on. So let's connect our Ferris wheel example to finding points on a circle. Since we were talking about various points on that Ferris wheel, which is a circle, so what we want to do is to see if we can sort of translate between the various heights versus time as we move along this Ferris wheel into a nice smooth curve. So let's take a look here. So we're going to see that the height above the ground at any point here is going to correspond to a y value. So if we know the y values as we move along here, then we can plot those heights along a horizontal axis for a particular angle. We're going to call that angle theta. And we also know that the y values for a point on a circle translate to which trig function? Sine, right? We know all of the y values here correspond to sine, right? So what we're going to do here is we're going to think about a unit circle, our favorite, because that way we don't have to get involved with r times the sine of theta. I mean, yeah, we just can put in the sine of theta here for the unit circle. Okay. So we know our famous points here are pi over 6, pi over 4, pi over 3, and then pi over 2. So we can take each y value here and start a plot. The height, this height right here, is the sine value of pi over 6, and that could be graphed right there. Forget about the rest of this graph for a minute. That's this height here and this height here are the same. Then we could move up to pi over 4 and we could calculate that height and translate it over here, put the point in. Then the height at pi over 3, and translate it and put it over here. And we could continue until, now this last point is pi over 2, and that's our maximum height of 1. So we know right here at pi over 2, we're at 1 on our unit circle. So let's list some values right here in this little table for the sine function at a given angle theta. So let's see, we've got pi over 6, pi over 4, pi over 2. Then what do we have? What would be the next one after pi over 2? 2 pi over 3, 3 pi over 4, 5 pi over 6, pi. And this keeps going. We'll just stop it there for a minute. That should give us some good values. So the sine of pi over 6 is 1/2. The sine of pi over 4 is square root of 2 over 2. Sine of, oh, we forgot something. Pi over 3. Scoot back. Oh no, can't forget pi over 3. Okay, so here's pi over 3, pi over 2, 2 pi over 3, 3 pi over 4, 5 pi over 6, and pi. All right, so 3 pi over 2 over 3, it's square root of 3 over 2. Pi over 2, we're at a high 1. And then 2 pi over 3, we're at square root of 3 over 2. 3 pi over 4, we're at square root of 2 over 2. 5 pi over 6, 1/2. And then pi, we're at -1. We'll stop there for a minute. So let's start graphing those points. So we got those points. Might as well take a little picture of those, put it on the next page. Oh yes, we're doing sine, not cosine. Thank you. I'm already like in my mind onto the next one, which is the pi. Yeah. Okay, so we've got that. Let's take a picture. Thank you, Hazel. We'll just take a little snapshot of that. Send to a new page. Now we want to graph this. So let's take a look. It's really slow. It hasn't even given me my picture yet. Come on. There we go. All right. It's amazing how impatient we can get with wonderful technology. Okay, so our next task is now to graph y equals sine theta and cosine theta. So I'm just going to superimpose this graph right here so we don't have to, this table, so we can just sort of do our thing. Okay, so anytime there's going to be really 5 important points when you're graphing sine and cosine. However, I'm going to put in a few more points for us. We know that sine goes through its whole cycle, one complete cycle, in 2 pi radians. So I always start with my beginning of my cycle and the end of my cycle. So I start at 0 radians, and I know I come right back to the beginning at 2 pi. I always first put in my midpoint of that cycle period, and then I put in my midpoint, which is really my quadrantal angles from that point. And then we know we could do our pi over 4s in here. We could cut them in half again, and we can, even go further. So given that this is going back now to the idea of the 12ths, given that these are in 6ths and 4ths and 3rds and halves, let's just make everything in terms of 12ths so we can get a good sense of where we are. So this is pi over 6 is 2 pi 12ths. Pi over 4 is 3 pi 12ths. Pi over 3 is 4 pi 12ths. So just fill this in for yourself. I'll shut this off. We don't really need to. Let's take a look at that. That's kind of this was something that Ian put together. And here we have our unit circle, and I've got my little directions here. This gets pretty complicated. So we have our unit circle, and notice we are now looking at the sine curve. So we're looking at keeping track of this vertical height over some angle here. As theta grows, we can see what happens to our height. So what I'm going to do right now is I'm just going to drag that height, as you see, as our angle of theta. Remember, here's our angle theta right here. As theta gets bigger, the height of our line segment gets bigger and bigger until we reach the tallest one. And then now theta is continuing to grow, but our reference angle now, which is the angle that's formed right here, right, between that point and the x-axis, this angle is decreasing, even though my overall theta is increasing, my reference angle is getting smaller, so my height is going to start shrinking back down to 0 at that point. And now my angle is getting bigger and bigger and bigger until I reach -1. Now my angle starts to decrease again. Okay, so let's go back and try this again, but let's actually trace out. Now this is the part that's tricky. Okay, so I want to trace out this vertical distance, so I click on that. And let's see if I can remember. Do I come back here and let's try it. It's Control T for trace. And let's see if that works. Nope. All right. Now I got to undo this. Boo, I tried to do it fancy. So Control Shift E. Did I highlight that? Yes. And then, all right, let's just try this. We'll just do the point then. Hit that. But I have two things hit here. That's the problem. Then I say trace. Then I undo that and do this. I think this works. Let's try it. There we go. So you can see your heights coming up. It's going down and it comes back. Is that cool? I think that is so cool. All right, so there's your sine curve, folks. There it is. That's one complete cycle of your sine curve. Notice it starts at 0, it builds into a height of 1, it decreases back to 0, then it decreases to a low of -1, and right back at 2 pi, you're right where you started, and this thing just keeps repeating and repeating in both directions. Same exact pattern. Okay? That's sine of theta. So I'm going to give you a quick view of cosine of theta. And you can go through the same process we just went through with the table and do cosine of theta. But let's just think, at 0, what's the cosine? What's the x value when you're at 0 radians? You're at 1, 0. You're out here. So your very first point for cosine starts up here at 1. So a lot of people think of cosine as a horizontal shift of sine. You could use your transformations idea. It's exact same pattern. It's just being shifted to the left. Pi over 2 units, radians. All right, so let's hide that. Oh, come on. You're supposed to work when I say hide. All right, let me try hide now. Hide the sign. Let's show cosine. So now cosine, we're measuring this horizontal distance, which is now this distance here. So as we go along the unit curve, think about what happens to cosine. It starts out as its biggest value, 1. Oh, over here. And then as your angle theta is increasing, that horizontal distance is getting smaller and smaller till it becomes 0. And then it increases again, and then it decreases. So that doesn't show us anything because I didn't put any trace on. We're just looking at the vertical. So let's try this again. Okay, now I do trace. I think this works. Now let's try it. No. Where did I? All right, so what do I do now? There we go. So sine starts at 1, decreases to 0, decreases to -1, and then comes back over here. Okay. So you can play around with that same idea right here, or you could sneak to the end of this where I have sine and cosine. Okay. So cosine starts at 1, goes downhill to -1 at pi, goes back uphill to 1 at 2 pi, and just repeats forever and ever. That's cosine. Sine, if we're looking at our vertical axis, we could look at any point along here, but if we look here as our starting point, we go uphill to 1, then down back to 0, to -1, and back up to 0. Okay. So these two curves have the same shapes. These are sinusoidal graphs. That's what we call sinusoidal. Now, just for your reference, I have a few different graphs listed here for your reference that you can look at later. We're going to graph a couple of these now, and I better book it because it's almost time to stop talking. So let's take a look here at number 10. I think that's where we are, right? Okay. Oh no, I haven't covered properties. Okay. So what's the domain for these two curves? I can put any value into this function, any real number. So the domain is -infinity to infinity. The range goes from -1 to 1. The period for both of these functions repeats starting at 2 pi. So it goes from 0 to 2 pi and then starts all over again. Even the cosine function, which is right here, 0 to 2 pi. If you take your two peaks here, that's a distance of 2 pi radians. So our period is 2 pi. Our midline for both of these, beautiful. X-axis here goes right through the middle, y equals 0. The amplitude is the distance from my midline up or my midline down to my lowest point, so that's 1. Now let's look at our symmetry. Our cosine has what type of symmetry? You can take this cosine function to the right of 0, flip it over the y-axis, and you have a corresponding point on the left-hand side of the y-axis. So this is an even function. It has even symmetry. And if you recall, this is just like a parabola. So the cosine of the opposite of t is exactly the cosine of t. When you put in opposite inputs, your outputs are exactly at the same output place, so the same height, if you want to think of it that way. And sine t, let's look at sine t. If I take this point, it actually comes down to here. See, 1 comes down here. When I go 2 of these spaces to the right and I go 2 of those spaces to the left, I get opposite y values. What kind of symmetry was that? Odd, or symmetry about the origin, right? So the sine function is odd. Sine of t is an odd function. And just look at that point there and that point there. They're the same distance from 0. It's an odd function, has symmetry about the origin. And that says when you put in the opposite of t, you get the opposite sine value. Okay, because here you're at pi over 2 and +1. Here you're at -pi/2, and now your output values are also negative. So when you put in negative inputs, your outputs are negative, and that's what this says. Negative inputs, your outputs are negative. All right, let's take a look at the very first graph here. So we're going to try to sketch the graph of half cosine of t. Notice we've changed our input from theta to t. Sort of works a little more familiar with our function notation where we have x or some variable in there. Okay, so we observe, if we go back to our transformations, here's our output value, cosine of t. This is on the outside of cosine. It's post-operation. It's half. It's going to affect what values? Inputs or outputs? Right. This is a vertical compression or shrink by a half. Okay? It's a vertical compression or shrink by a half. So this is a vertical shrink or compression, whichever word you like to use. And to get that, I am going to multiply all y values by 1/2 or divide by 2, however you like to think about it. Okay. So the first thing I'm going to do is do my cosine function, a real quick sketch of my cosine function. At 0, I start at 1. At pi over 2, I'm down to 0. At pi, I'm at -1. At 3 pi over 2, I'm back to 0. And at 2 pi, I hit my high point again. So here we go. Okay. And then you can just start this all over again if you want. You know, this whole thing just keeps repeating and repeating and repeating and repeating that way. And similarly here, this is, we know, has beautiful symmetry, right? Even symmetry. So there's cosine. So this is y equals cosine of t. So if I now just take all of my points, my outputs, and squish them, compress them, my value of 1 goes down to 1/2. 0 stays at 0. Half of -1 is -1/2. 0, 1/2. So now you get I didn't do a very good job there. There we go. Okay, so there's our compressed cosine. This is y equals 1/2 cosine of t. So the only thing here that got affected, our period is still the same. We still go from 0 to 2 pi. Our period hasn't changed. But certainly our amplitude has changed because our midline here is the x-axis, and our amplitude with cosine was 1, but now our amplitude is 1/2. That's the height, that's the maximum height between your midline and your peak or your valley. So we observe that multiplying the front of either sine or cosine by a constant affects the amplitude. So this is your first definition. I told you we're going to look at amplitude, period, and midline. So here's an example of the amplitude being affected. So here's your constant out front of either your sine or your cosine, and your amplitude is always an absolute value, because you don't want to say it's 1 and -1. It's always we don't care about the direction, just the magnitude. So we put it in absolute value. So whatever the coefficient is out here, you take its absolute value and you get the amplitude. Here's the next sketch. We have sine of t take away 1. So again, you want to get in a quick sketch of sine of t. So we're at 0, we're 0. At pi, we're at what? 0. And at 2 pi, we're at 0. At pi over 2, we're at 1. At 3 pi over 2, we're at -1. So we just get a quick sketch of sine in. Though you always want to have those 5 points, whatever your period is, the beginning and the end, and then halfway, and then halfway again. Those 5 points, no matter what the length of your period is, will always be critical for graphing. So that's one cycle of sine t. It's not the whole thing because it goes infinitely in both directions. Now it says calculate all your sine values and then take 1 away from them. So, okay, I'm at 0. I'm going to subtract 1, so I would be down here at -1 to start my sine t minus 1. Here I am at 1. I'd be at 0, -1, 0, -1. So here's sine of t minus 1. So you can see it's just been shifted down one. Oops, I screwed up. Sorry. I was like, that's not right. Missed this point right here. This should be at -2, right? Am I right? Okay, so it comes down like this. There we go. So you see, same shape, just everything scooted down 1 unit. So what's affected here? Your midline. Because in sine, the red graph, your midline is the y-axis. So if everything's shifting down 1 unit, your midline has to shift down 1 unit. So your midline now is y equals -1. Okay. So notice your midline is a constant that's outside what you're used to calling your vertical shift, right? So you would have it outside your constant. So either a sine t plus k or a cosine t plus k. And it's the line y equals k. Remember, it's always an equation. So I've got to speed up a little bit here, folks. So we're just going to talk about this next one and graph it. We're going to go back to our transformation ideas. I was going to try to show you again why this all worked, but here we're affecting our input. This is inside the function, or it's pre-operation. It's a horizontal effect. You're multiplying this by 2, so you're actually shrinking this by half. So you're going to get a complete period of your sine, and instead of 2 pi radians, in half the distance pi radians. So this is a horizontal compression or shrink. And what you do is all t values are multiplied by 1/2 are divided by 2. So if we were graphing this, again, we have our sine. This goes from 0 to 2 pi. This is pi. Pi here, pi over 2 here, 3 pi over 2 here. So that's a typical sine function. Now, if you think about it, 2 pi brings us back. I'm going to try to show you why this works anyway. 2 pi brings us back to 0. So this thing is going to come back to 0 when 2t is equal to 2 pi. When 2t equals 2 pi, we'll be back to our beginning point again. So if you divide both sides by 2, you get t equals pi. So that tells you that your entire cycle happens in pi radians. So that means you just take this entire cycle and it all happens from 0 to pi. So you chunk it out just like you did here, your halfway point, right? Your 1/4 point and your 3/4 point. So let's see if we can do it. 0 is 0, pi over 4. What would we be? 1. We'd be at our high point. Because look, if I put pi over 4 in here and you double it, you're at pi over 2. Okay. And at pi over 2, where am I? At pi. Okay. And at pi, I'm right at the beginning again, right? Because when you throw a pi in there, it's sine of 2 pi, which is 0. So your period is affected now. So that horizontal factor there compresses, makes your period shorter. If it's a whole number, and if it's a fraction, it stretches it. It affects your period. So B is the letter we use, capital B. And to find your period, you take your original cycle, 2 pi, your first, that's the period for your regular sine or cosine, and you divide it by the absolute value of B. So here we have 2 pi divided by 2 is pi, and that tells us our period. Right? So we just sketched it here instead of here. You could maybe later just spread it out a little bit for yourself. It would still have the same period. It just would be reflected. Okay, reflected. All right, I got to do one more for you, and then hopefully I'll give you a little time. So how about if we tried something with multiple things here? How would we approach this? 3 times the cosine of pi over 5 times t. Well, always, always, always start with your original function, cosine of t. Get a quick sketch of cosine of t on your graph. So you're going to have a 0. You're going to have a pi over 2. You're going to have a pi. You're going to have a 3 pi over 2. And then you're going to have your 2 pi. So you want to do one cycle of cosine on your graph. You know at 0 you're at 1. Right? You know at pi over 2 you're at 0. You know at pi you're at -1. Oops, I got to put a axis down here, so equidistance hopefully. Where's my black one? So here we're at 1, here we're at -1. Okay, so at pi we're at -1. 3 pi over 2 we're back to 0. And then at 2 pi, is that right? 2 pi we're back to where we started at 1. So again, here's your cosine. Notice your concavity as I graph this. Starts concave down, goes concave up, and then back to concave down. So that's cosine. The next thing I would do is deal with my period. Okay, my period. So this thing is going to affect the graph. So it's 2 pi. So my period is 2 pi divided by the absolute value of pi over 5. Absolute value of pi over 5 is pi over 5. So this is 2 pi times 5 over pi. The pi's cancel and you get 10. So you got to have that in mind. But now my graph is very different. So I would now start a new graph. And I would, so I'm just going to erase what I have. And do the same thing I just did for you, but now with this period. So, okay, so now instead of going from 0 to 2 pi, I go 0 to 10. I still chunk it out. I go halfway at 5. Now remember, that's like pi. And then halfway again is 2.5. This is like pi over 2 and 7.5. Okay. And I don't think about that 3 out front at all. And I think about what this looks like that. That's just cosine of pi over 5t. And now I triple all my points. So instead of being at 0, 1, I'm going to be up here. Let's make it purple at 0, 3. And instead of being at 2.5, 0, I'm at 2.5, 0. Because when I multiply 0 by 3, it doesn't matter. And then instead of being down here at 5, -1, I'm way down here at 5, -3. And I come up here, and then I'm up here. So you see this whole thing has been stretched. The period has changed, and it's been vertically stretched by a factor of 3. Okay, so that's that one. All right. So you have a lot of practice. Most of the graphs that I've asked you for in here and afterwards are on that reference sheet. So I've given you 5 graphs. Unfortunately, I only have 5 minutes, but I knew today would be long. I was actually thinking of not giving you any lesson activities, but I thought that might be dangerous. So look at the graph. See first, if your graph along your vertical axis starts at your high point, you know it's which sinusoidal graph, cosine or sine? It's cosine, okay? So you know that's some kind of cosine function. This is sine, but look, it's going down instead of uphill. So hopefully just find some points and think about your transformations. Try to do these. Give these a really good effort before you look in the back at the answers, because that's going to take something away from your learning, okay? So give it your best shot before you look at the back to see the answers.